In realms of qubits, a future untold, where quantum whispers and mysteries unfold. A double-edged sword for the world in strife. Can quantum computing mend or cut the life? Can progress solve or just devour more? Quantum answers lies at our core. And to guide us through this insightful session, we have Dr. Harish Sahu, Scientist E, DRDO, Delhi, a leading expert in cybersecurity, cryptology, quantum computing, and quantum cryptography. Dr. Harish Sahu has 20 years of experience in R&D sector, has worked on national projects and collaborated with industry and academia. Dr. Sahu has received numerous awards, including the Best Industry Expert from Amity University in 2018, Lab Scientist of the Year in 2019 for his outstanding scientific contribution. He is one of the distinguished experts for AICTE for review of Atal FDPs and Parak project. Professor Sahu will be sharing a talk on quantum computing and application. So please welcome Dr. Sahu.
Good afternoon, everyone. Thank you for nice introduction, and thank you, Smriti ma'am and Honest team for inviting me for this talk today. So today in this talk, we will be seeing this quantum computing and its application in variety of domains. And how many of you are aware of about this quantum computing or quantum mechanics, or how many of you are aware? So let it be interactive. So someone can come forward, maybe that will be good. She can come forward. Yeah, please. So let it be interactive, this talk, and at the end we should learn something. Should not like that I am speaking and you are just listening, and at the end you will say, oh, we do not understand qubit, how qubit works or something. So I will try to make it as simple as possible, and I have cut short my talk because of the time constraint today. But we will be trying to cover what is the fundamental of this quantum bit, quantum gates, and this quantum algorithms, and their application in variety of domains. So I will try to keep it as simple as possible. At the same time, I will be conveying the core concepts and how it will help in variety of domains. So am I audible to everyone?
Yes.
So the original agenda was like this, that first we will be covering this quantum computing and few fundamental principles on which this quantum computer operate, and then about quantum algorithms. So there are two primary breakthrough quantum algorithms which makes something easier for us, and vice versa also. So these quantum algorithms have an effect on cryptography. So some of the cryptographic schemes can be broken using this quantum algorithms on a quantum computer, and we will be discussing how to counter it. Then we will be seeing quantum safe cryptography, means in advent of this quantum computing era, we want to have a safe encryption schemes. Then quantum simulation. So in this quantum simulation, some things like if you want to design efficient batteries, then on normal classical supercomputer, you cannot have those kind of designs possible. But on a quantum computer, you can do variety of this kind of simulation very easily. Means if you want to design efficient battery, then you can do it. If you want to design some particular metal or the material with certain properties, that you can do very easily using quantum computing. And then we will see recent developments in this domain. So let's first start with this, how this quantum computing is different from the classical computing. So it's totally different. And it is based on two important phenomena, quantum mechanical phenomena. Those are called superposition and entanglement. So anyone have idea about superposition? Yeah, can you please tell?
So any quantum mechanical
slightly different from the classical bits. So classical bits can be either 0 or 1 only. At the certain time, it will be either 0 or 1. In classical computer, bits are either 0 or 1. But in case of quantum bits, it can be in combination of both 0 and 1 simultaneously. Maybe it is not easy to understand first time that it can be both 0 and 1 simultaneously. In a quantum system, it is there. But once you measure it, you will get either 0 or 1 on measurement. But in a quantum system, this qubit can be in. So am I audible to everyone or not?
Yes. Yes.
Perfectly audible?
Yes.
Yes. Okay then. So this is the fundamental difference that it's based on quantum bits, and this quantum bits can be having both 0 and 1 simultaneously.
Yeah. Hello? So maybe we Hello? Is it fine now? Okay. So, is it okay? Yeah. So this superposition, what I was telling is that the classical bits can be either 0 or 1, while in case of quantum bit, it can be both 0 and 1 simultaneously. Once you measure it, it will be either 0 or 1 with certain probabilities that we will discuss. So, if there are n qubits, then we will have 2 power n basis states. Like in case of single qubit, we have 2 basis states, namely 0 and 1. So it is basically linear combination of 0 and 1. Once we will have n qubits, then there will be 2 power n basis states, and it will be in superposition of 2 power n states simultaneously. So let's see. So superposition, just now I explained to you that the single qubit here phi So it can be linear combination of both 0 and 1 simultaneously. Simultaneously word is very important. So when you have it is in quantum system, it is both 0 and 1 simultaneously. But when you measure it, you will get either 0 or 1 with corresponding probabilities. And those probabilities are getting 0 probability is mod alpha square. So what is this mod alpha square? It is probability of getting 0 on measurement. And likewise, mod beta square is probability of getting 1 on measurement. And this probability sum is 1 for a single qubit. Okay? So in single qubit, you will not be able to appreciate it, but once we move from single to many qubits or n qubits, then you will realize the potential of this phenomenon. So single qubit, let's understand in one other way. It's a block sphere representation to understand the single qubit system. So like in classical we have 0 and 1. Here we are also having 0 and 1. And it's a unit sphere. So every point on the surface of this sphere is a valid single qubit state. Okay? So this psi is a valid single qubit state. So all points on the surface are basically single qubit states. And if you want to have classical 0 and 1, then north and south pole are basically your classical 0 and 1. In between, every point on this sphere can be described as a linear combination of 0 and 1, like alpha times 0 plus beta times 1, or maybe in theta forms, there's two angles are there, theta and phi. Using those two angles, you can uniquely define a state psi on the surface. Okay. And the probability sum is basically this coefficients. 0's coefficient is alpha and 1's coefficient is beta. So this alpha and beta are basically amplitudes. And this mod alpha squares are basically probabilities. And the probability sum will be always 1. So there are two ways to represent the qubit. Another way is in forms of these angles theta and phi. We can represent every point of the surface. Okay. So understand that at some point on this this equator. So what will happen on the equator? The state on the equator is equidistant from both 0 and 1. It is in between. So we can either on measurement we will either have 0 or 1 with equal probabilities. Okay. So on equator a state can be written like this. If you want to write a state on equator, that will be basically this. So that is basically 1 by root 2 0 plus 1 by root 2 1. So I am talking about a state at this point plus x point. So what will happen is that once you measure this qubit, you will either get 0 or 1 with 50-50 probability. Why? Because this is amplitude, and if you square, that is basically 1 by 2. So the probability is 50-50. So single qubit, if you are clear, then we can move to multi-qubit system. Then you will be able to appreciate the benefit of the superposition property. So any doubt over this single qubit representation? So let it be interactive. If any doubt is there, then you can ask. Yeah, so like in classical computing, we have classical gates like AND gate, OR gate, NOT gate. So here also in quantum, we have quantum gates. And what basically these quantum gates are? There can be single qubit quantum gate and multi-qubit quantum gate. So single qubit gate, what it does is, it just changes the position of this state from one place to other. So if I apply some quantum gate, suppose, and it moves this state to some psi dash position. So basically you are applying some operation U, or basically the quantum gate, on the state psi, and you are getting some state psi dash. Okay. And if you want to compare it with this classical thing, then if you apply some NOT gate on 0, then what you will get? If you apply NOT on 0, what you will get? 1. So basically what happening is, some rotation is there. So on this block sphere, this state is rotated and it is coming here. So every single qubit quantum gate operation is basically just rotation over this block sphere. You can understand in this way. So likewise in classical we have gates, here also we have gates. Okay. And these gates can do all the things which are possible in classical, but it has more things. Like here we have this gate, Hadamard gate. So it creates equal superposition states. Means if you start with a 0 state, then you apply Hadamard gate, then it will move the point to equator. On equator, you will see that in class originally it was 0, but when you apply some Hadamard gate, it is basically this kind of state. And that state is having both 0 and 1 in quantum system. Okay. So there are other gates also. So basically to implement some quantum algorithm or some application, you need quantum bits and quantum gates. So once you are having these two things, then you can implement quantum algorithms or quantum programs on a quantum computer. So superpositions for single qubit we have seen. Now if we move from 1 qubit to n qubits, then what will happen? In n qubits, there will be 2 power n basis states. What are basically basis states? Basis state like single qubit 0 and 1. If you are talking about 2 qubits, then there will be 4 basis states, namely 0 0 0 1 1 0. So in mass term also, yeah. So any 2 qubit system can be described by these 4 basis states. So similarly for n qubits, there will be how many basis states? How many? 2 power n. So we are having n qubits. N qubits, and there are how many states? 2 power n. And what are those? Up to n times 1. Okay. So see here, we are having only n qubits, but we have superposition of 2 power n state space. So see here, this phi n is basically linear combination of all these 2 power n basis states. we are writing those states in decimal numbers. So here basically this capital N is nothing but 2 power n. Okay. So there are these 2 power n basis states, and n qubits can represent all of them simultaneously. Okay. And the condition will remain same, that the probability of this all state sum will be 1. So if I ask you what is the probability of getting 1 on measurement, that will be basically this amplitude mod square. So alpha 1 mod square, and sum will be 1. Okay. So if I ask you, can you have this 4 qubit resistor and equally superposition, means all of the states probability is same. So if I ask you that how many basis states will be there for 4 qubits, 16 will be there. Those will be basically 2 to the power 4 and starting with 4 0 up to 4 1. So we can have this kind of state. 5 4, that will be looking like this, 0 0 0, that's 0 0 0 1, and likewise up to 4 times 1. And there will be some amplitude associated with it. So it is, let's suppose it is 2 power 4 root. So if you see here that there are all basis states there in 4 qubit, and the amplitude of all state is same, so the probability will be also same. And what is that probability will be? Basically square of this coefficient or the amplitude, that is 1 by 2 power 4, means 1 by 2 powers 1 by 16 is the probability of each states. So the thing here which I want to emphasize here is that having only n qubits, we are having state space of 2 power n, that is exponential. Suppose if you put the value of n is equal to 100, then how many basis states will be there? 2 power 100 states will be there. Although we are having linear qubits, only 100, but the state space is too large, and that is exponential 2 power 100. So that is the power of a quantum bits, or basically quantum computer, we will see in just a while. So just keep this thing in mind, that using n qubits we can have 2 power n states simultaneously, or we can cover that much large space. While if we are in classical, then what will happen? Classical n bits are there. So what they can store? They can store any of the basis states. Maybe it is 0001 or any of those 2 power 4 combinations, but only one at a time. See the difference? In classical, 4 bits can have only any one of the possibilities out of those 2 power 4 possibilities, but in case of quantum, it can hold entire space simultaneously. So that thing is okay. So probability is what? The amplitude or the coefficients mod square, and the sum will be 1. So if I ask you what is the probability of getting 0 state in this combination, that will be alpha 0 square. So keep this thing in mind. So once this thing is in superposition, it is in quantum state. But when we measure or observe it, we will get any one of those 2 power n states with associated probabilities. So we will get one of them with associated probability. Okay? Maybe in quantum all things are there, but once you measure it, you will get one of them. So now come to the important property of quantum parallelism. So we are clear with the superposition property that we are going to use for this thing. So if I want to compute some function f, okay, in a classical computer on this 4-bit values. So how many 4-bit values are there? 2 power 4. And I want to compute a function on all these 2 power 4 values on a classical computer. So what I will be doing is, I will be calling this f for different inputs. So there are 16 inputs, so I will call this function 16 times to compute the f on different 16 values. So if you see in normal computer, we are doing things in basically sequential manner. For all possible inputs, you will be trying one by one. Okay? But in case of quantum, what will happen? We have only 4 qubits, so we can create superposition. Once we have superposition, it means we are having all states with us. So see here, like I can create this kind of state. Just how I explained to you, everyone. So these kind of superposition, suppose I created for 4 qubits. So there are 16 basis states and its superposition is there. If I want to compute the same F on a quantum computer, then what I will be doing is, I will be applying this F on these 4 qubits. But what will happen, because these 4 qubits are in superposition of all states, so this F will be computed on all possible values of 4 bits. So while we are applying this F one time on this 4 qubit system, but in turn it is being computed on all possible values of 4 bit strings. So in one go, this F is computed on all possible 4 bit values. See, understand the difference? In classical, you have to call this function every time, one by one, for different inputs. But in case of quantum, in one go, it is being applied on all of them. So F of 000 is calculated, F of 001 is calculated, F of 11 is calculated in one go. And that is the thing is called quantum parallelism. So this makes a quantum computer faster than classical computer. Why? Because the thing which is taking exponential time here in normal computer is done in one go on a quantum computer. So 4 qubits you are not able to, how many times it is faster basically? If I say that quantum computer is how many times faster here than the classical? 16 times? Correct? But here we are talking about the 4 qubits only. Suppose if we increase the number of qubits from 4 to 100, then what will happen? So 2 power 100, and 2 power 100 is a very large number. So this superposition phenomena makes this quantum parallelism possible, and this quantum parallelism is the key which makes quantum computer faster. So this is the core fundamental we should be clear with. If anyone has any doubt, then can ask me, and if someone want to sleep, then they can go. You can go. Please have rest. So, quantum parallelism is clear to everyone, or any doubt is there? Frankly, if it is clear, like clear, otherwise I will ask like sir has asked earlier. Tell the Rashtragan. So far if this thing is clear, then we can, other things are very easy to understand. But here one catch is there. So when you measure it, you will get one of them. Maybe you are in quantum system, we are having f of all values, but when you measure it, you will get some particular with some probability. So entanglement right now we can skip. So this is the quantum computer architecture. See here, these things are basically the hardware there, but basically we will be talking on the software or logical layer. So this quantum computer can be implemented using variety of qubit topologies, superconducting and ion trap and other things are there. But we should not worry today on the how this is being designed or made. Our concern is that we have a quantum computer with number of qubits, what we can do on that. So the important role of this quantum algorithms come into picture. As we have seen just now that quantum parallelism is there. We can compute the f parallelly on so many values at one go. But how to do the meaningful computation? Because see here one catch was there, that when you measure it, you will get one of them only. So what you want? You want your problem's solution in one of them. Maybe you are looking for some solution, like you are searching for some minimum thing, f which f is minimum. Then what you want is, after doing this superposition and some quantum algorithm, you want to have the minimum value to be having high amplitude or high probability. So quantum algorithms you want to design in such a way that solution to your problem should have increased amplitude and increased probability. Because see here, all f are equal probable here, because the coefficient is same for all of them. But what we want to do is, we want to make sure that whatever our problem solution is there, it should have higher amplitude and higher probability. And you know, once, because the probability sum is 1, if you increase someone's probability, then others will be decreasing, because the sum is 1. So, here is the trick in quantum algorithms which somehow do this thing, that how to increase the amplitude of desired solution. That is the trick. That's why we do not have so many quantum algorithms after 3 decades or so. Why? Because how to do that thing intellectually, and it should be providing the solution, and it should be faster than the classical solution. Okay. So this quantum algorithms play an important role. Okay. And there are 2 breakthrough algorithms, Shor's and Grover's quantum algorithms, which does something which is very hard for a classical computer, even for supercomputer. But this Shor's algorithm and this Grover's algorithm on a quantum computer makes those things very easy. We will see in detail. So these are key quantum algorithms. So it started with 1982 when Richard Feynman, a famous quantum physicist, presented a paper in which it says that if you want to simulate some quantum mechanical system, then you cannot do it efficiently on a classical computer. So in 82 he gave the idea that to simulate a quantum mechanical system, you should have a computer based on quantum mechanical phenomena. So basically he has given the idea of quantum computer at that time, that if you want to simulate some quantum mechanical system, like you want to design an efficient battery, or you want to design an efficient molecule, or if you want to understand some chemical process, or want to design something, drug or something, whatever you want to design, so there are some quantum mechanical interactions are there. So if you want to simulate those kind of things, then classical computers are not the right choice. They cannot do it efficiently. So for that, a system based on quantum mechanical properties such as superposition and entanglement we should have. So in 82 he has given the idea, but that time progress does not happen. But in 92, Dios and Joseph, 2 scientists, has given some quantum algorithm. If it is run on a quantum mechanical system or quantum computer, then it solves that problem exponentially faster. Okay. So what was the idea there is that if you are given some function f, and property is that it is either balanced or constant. So if I give you a function which is either balanced or constant, then you require exponential trial to make sure that. But their algorithm can do it in one go, like quantum parallelism I just now explained. So they compute this f only once and able to tell that this function is either balanced or constant, whatever it is. So you must be aware that this f, x1, xor, x2, is it a balanced or constant function? Anyone please? Balanced. Because half the time we are getting 0 and half the time you are getting 1 on the all possible inputs. So, and maybe this function can be complex. We are taking a very simple example. So if you use this, so if you want to check it, that whether it is balanced or constant, then how many trials you will do to make sure that this is this? One trial is sufficient? How many trials do you have to make? So, okay, tell me how many possibilities are there? How many trials, how many possible inputs are there? There are 4 inputs, 0, 0, 0, 1, 1, 0, 1, 1. So 2 power 2 inputs are there. So how many inputs we must try? The function is having these 2 properties, balanced or constant. So at least half you need to try, or so if you try half the inputs, then still you are not sure. because half the input support you are getting 0 0. Half the possible inputs you are getting 0 0 0 every time. Still you are not sure whether it is balanced or constant, because it may be all zeros, or it may be like first half are 0 and second half will be 1. So half the inputs plus one input, then only you will be sure that this function is balanced or constant. But the same thing, so suppose this is n bit function, then how many inputs you need to try? 2 power n divided by 2 means half the space, half the input space plus 1. But on a quantum computer, only one trial. One time you just compute this app, it will tell you. So he did some clever things in his algorithm, so that on this superposition and quantum parallelism, we will get some output, and based on that, he will be able to tell. So see here that something is exponential for a classical computer, but for a quantum computer, it's a one trial. Means this function need to compute it this many times, 2 power n by 2 plus 1 time, but on a quantum computer, only one evaluation of f is sufficient. So maybe one small example, it is not clear, but if you have a very large n bits inputs, then you will see the benefit. So this was the first quantum algorithm, which showed that this quantum computer can do things exponentially faster, which are not possible on a classical computer. Then comes Peter Shor in 1994. He has given a quantum algorithm for integer factorization and solving a discrete law problem. So integer factorization, as you all are aware, that multiplying is very easy, but factoring a large number is difficult, and the complexity is basically sub-exponential. So it's like if I give you some 2000 bit number, then even the using supercomputer available today, you cannot do it in thousands of years. To factor a 700 digit number only, if I give you a number 700 digit number, and I am telling you that this is a product of two prime numbers, then factoring that number into those two primes is sub-exponential complexity. And even the best computers available classically, we cannot do it in reasonable time. But on a quantum computer with hundreds or thousands of qubits, you can do it in half an hour or so. See, at one place you are saying that the best supercomputer available you can take, also you cannot factor that number in a reasonable time. It will take thousands of years. But on a quantum computer, the same problem can be solved in half an hour. Very small quantum computer with only thousands of qubits can be done. So this Shor's algorithm solved that factorization problem, and other problem is the discrete law problem. And this has variety of implication in other domains, like in case of cryptography, where RSA kind of ciphers are dependent on that problem, that this factorization were hard and these ciphers were secure, but now they are not secure. So after this Shor's algorithm, people started developing quantum computer. The idea was given in 82, but no progress was made there up to 94, because there was no practical usage or interest was there. But in 1994, Peter showed that this quantum computer can threat to your cryptographic schemes that we will discuss. So then this quantum computer development started. So we will see that thing. Next is this Grover's algorithm. So what it does is, classically if you search and if you do not have any ordering, then the search space is suppose n, then you need to do a linear search. So if there are n items, then I ask you find this item. Then you will take how many trials? You will take n trials to get that thing. Okay. So that classically if you do this kind of searching, then it is how much time? If there are n items, then it is order of n. How we do it? Linear search. What is that? We search one by one. Okay. So that same thing can be done on a quantum computer using this Grover's algorithm in how much time? Square root of n. Okay, and this quadratic speedup from n to square root n is significant. Okay, that we will see in detail. But this search is everywhere. So whatever we do, basically we do search kind of thing only. If I am coming from Delhi to Greater Noida, so I was trying to find some optimal path based on time or distance. So there are n paths and I want to choose one of them. So basically I am looking for or searching for an optimal path. So it says searching only. Okay, so search is everywhere. Some database is there, you are trying to find something in that. So basically you are doing searching. So this searching is made efficient using this algorithm. But the thing is that in 94, 96, this algorithm was given in 1996. By the way, this Love Grover is an IIT Delhi alumni. And these two algorithms, Shor's and Grover's algorithm, has a huge impact on this domain. And after that, this quantum computing development tremendously started, got attention of every government and other companies' attention. And people invested money, and nowadays we are having a small scale quantum computers, and those are available on cloud also, so you can use them to run your algorithms. And then comes this quantum simulation. So we will discuss this quantum simulation in detail, but the idea here is that something like simulating a coffee molecules effect on our mind. A very simple thing. Coffee molecule is there, and its impact on our mind is a very hard problem for classical supercomputer. You cannot simulate or see the effects on our brain using classical supercomputer. But the same thing can be efficiently simulated on a quantum computer with hundreds of qubits. See the difference? Something is kind of impossible for a supercomputer, classical supercomputer, but can be done easily with hundreds of qubits on a quantum computer. So variety of simulation kind of thing. So like simulation, if we want to design some material with specific properties, so generally we do hit and trial kind of thing in classical thing. But if we have a quantum computer and somehow we can model those properties, then we can find those materials easily. Or maybe if you want to design an efficient battery, that also we can do on a quantum computer easily. That is kind of impossible with certain accuracy or precision which you want, the simulation on a classical computer. But that is easy for a quantum computer. Why? Because this superposition kind of thing. It can trace or it can track all possible combination parallelly. So this thing keep in mind. How this quantum computer works? It can traverse all state space parallelly. Okay. So there are variety of applications of these things. Like just now I explained, this factorizing very large number is basically application in cryptography. So some cryptographic schemes are designed based on this problem, and they are not safe. So whatever we are doing on mobile nowadays, so we do some e-commerce or banking, so we use RSA kind of encryption there to make our information secure. But those RSA ciphers which are based on integer factorization will not be secure when we have a sufficient large quantum computer with us. So true random number can generate using this quantum computer also. So basically random numbers are there, but these random numbers are not truly random, which we generate on a classical computer using some parameters. But if you have a quantum system, then those numbers will be perfectly random and you cannot predict them. For security communication, quantum key distribution is one domain. So that is there, in which what happens is that there are two, suppose units are there and they want to do a secure communication. So what they do is they just send some photons and encode their information on those photons and send from sender to receiver. This way, this kind of QKD schemes, whenever adversary try to look into those photons, then the recipient will come to know that there is an adversary present. If they are getting the correct qubits or whatever information they send, it means there is no adversary. So basically hack-proof kind of cryptographic things you can do using quantum particles. Search I already explained, and we will see again. Simulation already I explained. So let's go to Grover's quantum search algorithm. So just now we explained that search is very important. So when we go for linear search, when our data is not sorted. So suppose our data is sorted, then what we can do? Suppose your data is already sorted. Some numbers are there and they are sorted in ascending order. Then how you will search? Data numbers are there and they are sorted in ascending order. And I am asking you whether this number is present in the list or not. Then how you will do?
We'll take one number, then trial, then we'll take second.
No, ma'am.
We'll go to bit value and see.
Yeah. So what is that called? Bit value kind of thing? It's called binary search. No, it's binary search. See here that like in dictionary also we do same thing. Suppose these numbers are there 3, 13, 15, 18 or 29, 15, and I am asking you whether 18 is there or not. So these are sorted basically. So if I ask you 18 is there or not, so then how you will be doing? You will be pointing to the mid element. Okay, so I was looking for 18. Suppose this mid element is, let's put 17 here. So suppose this mid element is 17. Then what you will do is, you will compare your number which you are looking for to the mid element. If it is less, then you will choose the first half list. If it is more than that, then you will go to the second half list. So if I am looking for 18, then what I will be doing is, so I compare with middle element, that is 17. So I will go to the second half. Again I will do this thing iteratively. So again half the space, half the space. So if this entire thing is n, then in log n trials, log n time queries, I can find this. This is basically called binary search. So if data is sorted, then in log n time only we can do it. So it's very fast. But if this data is not sorted, which occurs in most of the scenarios, then we need to do linear search. Just now someone tell that we will be going one by one, and suppose the data is not sorted. So what you will be doing is, suppose these are the number. So what you will do? Data is not sorted. So either you will sort it first, then search, or you will just do linear search. Because sorting this data also takes some complexity. And that is how much? Sorting complexity is itself n log n. So if you do linear search, then it is log n. And if you have a quantum computer, order of n. Just a second, let me erase those things. Linear search, order n, and if you do the Grover's, then it is square root of n. So see here, this kind of scenarios are there, that some source to destination you want to go, then there may be n paths, and you want to choose one of them. So what you will do? You will search basically, whose cost is minimum or whose cost is optimal. Then you will search those paths and then you will choose it. So basically, everywhere searching kind of thing is there, so that you can do efficiently using Grover search. So what is the idea here in the Grover search? There are n elements. So what you do is you can create superposition, and the superposition creation is very easy. Just you initialize the qubits with zeros